Is the screen visible now? Uh, uh,
Yes, ma'am.
okay. Thank you for your cooperation. Uh, Welcome everyone for the fifth week problem solving session for the NPTEL course and introduction to climate dynamics, variability and modeling. Today we will solve a few questions based on the topics in the last 2 weeks. So this is the first question for today. What is solar irradiance? The total energy output of sun integrated over its entire lifetime. The rate at which the solar energy from the sun falls per unit area at the top of our Earth's atmosphere. The variation of sun's surface temperature over the solar cycle of 11 years. The reflection of sunlight by the Earth's surface and atmosphere. Which of the following options are correct? What is solar irradiance? You can unmute yourself or you can write your answer in the chat box. Yes, it is option B. The rate at which the solar energy from the sun falls per unit area at the top of Earth's atmosphere. So the correct option is B. And in the second question is, what is the average value of solar constant? That is mean solar irradiance at the top of atmosphere. What is the average value of the solar constant? Uh, 340 or 341 watt per meter square or 680 watt per meter square, 1360 or 1361 sometime in the both is given as the MCQ, and also 2990 watt per meter square. See, yes, this is 1360 watt per meter square. Question 2 option C is correct. And question 3, what is the global average value of solar energy received at Earth's surface considering after the atmospheric effects? Four options are given. You have to choose the most plausible option. First is the 1360 watt per meter square, 1000 watt per meter square, 240 watt per meter square, and then option D is 170 watt per meter square. This is coming about, this question is giving option 170 to 180 watt per meter square. Because you can see that in the first question was the solar irradiance, that is defined as the solar power that is received over per unit area at the top of atmosphere perpendicular to the sun. Now at for that fraction, some amount of accounting that can be averaged over whole earth sphere, that is 1360 by 4, that is 350 watt per meter square. And also another thing, there is an earth's albedo that is about 0.28 to 0.3, that number. So you can take that about 30% of incoming solar light is reflected by the clouds, aerosols on the earth's surface. So there is net 239 to 240 watt per meter square, that is absorbed solar flux at the total top of atmosphere. And at the surface there is this should be lesser than the 240 watt per meter square, because the atmosphere absorbs and scatters a part of it before reaching to the ground. So due to that calculation, the earth's surface receives about 170 to 180 watt per meter square of solar energy. Therefore, for the question 3, option D is correct. Now, if you have any question or doubt, you are free to interrupt me. Now, question 4. If solar irradiance at the top of atmosphere is S0, what is the global average irradiance on Earth's spherical surface? You can take a circular surface towards the sun, and then you have to for finding the global average value of irradiance, you have to divide it by the 4 pi r square whole surface area of the earth. So the option will be coming to the question 3, or option C is correct for this question. Question 5. Solar irradiance varies with from sun to earth or other planet. How it varies? Varies with d, varies with d square, varies with d cube, or varies with d to the power minus 2. Yes, question 5. This is d to the power minus 2 variation, and it is inversely varies with d square. Question 6. If Earth's albedo increases from 0.3 to 0.35, what happens to the absorbed solar irradiance? Assuming that S0 is 1360 watt per meter square. So S0 is the our incoming solar flux. We have S0 incoming, absorbing 0.7 and 0.65. Absorption before and after is about 0.7 and 0.65. So you can find the change, that is the 1360 can check 2. So that is coming 1360 into 0.5. Minus 1360 into 0.5. So there will be a decrease by 1360 into, so before this was 1360 into 0.7 before. After this is 1360 into 0.5 65. So this is 1360 into 0.05 factor decrease. That is question option 2 is correct. Question 7, if Earth's albedo decreases 90%, what happens, or the how much would be absorbed solar irradiance at top of atmosphere? Increase by 5%, decrease by 68 watt per meter square, no change, increases by some factor. For this question, any of this option cannot be, any of the option may be not correct, and we know that the alpha for the Earth is now 0.3 about, so you have to decrease it by 90%. So it will now go to 0. Decrease it 90%, so alpha nu, that is 0.3 into 0.9, 0.3 into 0.9, 90% decrease. So 1 minus 0.9 here is equals to 0.03. So you have the 1360 into 0.03, 1 minus 0.03, 1 minus 0.03 is equals to 19.2. So it will be decreasing if the Earth's albedo decreases 90%. Now the question, sorry, 8, the solar constant varies due to Earth's orbital eccentricity. The fractional variation is can be given approximately 0.033, 0.01, 0.001 and 0.1. Okay, something is missing here. Suppose eccentricity is given here also. Question, I guess there was an error in this question. Suppose the Earth's eccentricity is given. It varies due to Earth's solar constant varies due to Earth's orbital inclination. The fractional variation comes approximately in order of plus minus 2e, that is about 0.033 or 3.3%. Question 8, option A is correct. Question 7, no option is correct, but you can find the correct option because or the correct answer because alpha you know at 0.3 now, so you have to decrease alpha by 90%, so it will come from at 0.03. Now you have to find how much would be absorbed by the solar irradiance, so that will be 1 minus alpha into S0 now, that comes around 1320 watt per meter square. So there will be a decrease. Now question 9. On geological time scale, uh, in the slow increase of solar luminosity, that is about 100 mega year increase of 1% in 100 mega year, is observed due to fusion of hydrogen to helium in the solar core, orbital resonance with Jupiter, decline of Earth's magnetic field, increasing eccentricity. The geological timescale, the luminosity, the solar luminosity or the energy output from the sun uh, is not constant. It varies with time of about, suppose, 1% increase or decrease in about every 100 mega year. It is due to 1% decrease in every 100 mega year. This is due to please expand question 8. Okay. Question 8, you have to find the, the solar constant S0. So its variation is 0 and it is d minus e square. I have to write, I guess. So S is equals to S1 is equals to S0 by d minus e square 1 and S2 when it is at S0 by d minus e d plus e square. Now the fractional variation can be written as S1 minus S2 by S0. S0. S1 by S2 is upper and S0 is lower. So you can mathematically write it as 1 by d plus e d. You can take 1 AU unit, or I am just taking d. 1 by d plus e d minus e square, this term, minus this, d plus e square. You know how to solve this kind of equation. That is, you have to take common of 1 by this square from the two term. So 0 d plus e square 1 by this square. The factor is 1 minus e to the e by d square minus 1 by 1 plus e by d square, 1 minus e by d to the power minus 2. So this comes to 1 minus e by d to the power minus 2 minus of 1 plus d e by d to the power minus 2. This binomial expansion, 1 minus 2 e d minus 1 minus 2 ed. You have to expand this 1 by d minus e square minus 1 by d plus e square then you can find that there is a minus 2e expansion. This is expansion plus 2e plus 2e term remain here. So the solar constant now will be, the fractional variation will be plus minus 2e here. Is it okay, or I have to do
Yes, ma'am. Thank you, ma'am, for
okay.
your explanation.
Huh. And in question 9, on the geological time scale, the increase in the solar luminosity is due to, this is only for the output of the sun. On the geological time scale, the slow increase of solar luminosity is observed due to, this is only the solar luminosity value. You know the solar luminosity value, that is about 3.86 into 10 to the power 33 arcs per second, or you can in the SI unit it is 10 to the power 26 so coming. So this value changes only for the fusion of hydrogen to helium in solar core. Question 9 option A is correct. Question 10, what is the correct formula of the luminosity and the flux? That is, the solar luminosity is equals to 4 pi r square S0, or solar luminosity is equals to 4 pi 1 AU square S0. Solar luminosity is equals to 4 pi r square S0, and luminosity is equals to S0 by 4 pi d square. In Earth's case, which of the following formula is correct? S0 is the flux of sun at Earth's position, or at Earth. Sorry. Which of the following relation is correct considering the S0 is the flux at Earth?
Option was
Uh, Earth and the Sun's distance is 1 AU. So while considering Earth, the correct option will be option 2. And for any distance from S0 in our lecture, S0 is often denoted by the flux at Earth, that sense. So question 10 option 2 is correct. Now this is question, we should go to question 11. In 11-year solar cycle, the solar irradiance or the S0's value vary, and what is that variation? This is about 0.01%, 0.1%, 1%, or 10%. It has been observed that the 11-year solar cycle causes very small variation in the S0's value or the flux value of at Earth. That is about, variation is about less than 0.1%. It is found to be 0.01% variation. Now in question 13, is question 12. At what wavelength does the sun's irradiance peak? Approximately 280 nanometer, 500 nanometer, 1 micrometer, and 10 micrometer. For this question, you may need the the lambda t is equals to 3 into 10 to the power minus 3 SI unit, that formula. So from that formula, if you can use lambda t, lambda you have to plug in the value of lambda t there, t for the sun, that is about 5000 Kelvin, that comes around 600 nanometer. So this peak is observed at 500 nanometer. So Wien's law, you have to use the Wien's law. Wien's law. About 5000 Kelvin or 6000 Kelvin temperature of the sun surface. Now if you plug in 6000 Kelvin, then you will get 500 nanometer. Question 13. If S0 is 1360 watt per meter square, what is the irradiance at Mars? It is given that the 1 point Mars has distance of 1.52 AU from Sun. What is the value of the S0 at Mars? Yes, question 13. You will get. You can write this by, so is Earth is S varies to 1 by d square, so SE by SN is equals to 1.52 square by 1 square. So SN comes for the S Earth by 1.52 square. 1.52 square comes around 2.31. So 1360 by 2.31, this comes around 588 watt per meter square. So 588 watt per meter square. 13 option 4 is correct. Sometimes in such questions not the exact values are not given. You for that case you have to choose, in the MCQ option you have to choose the most closest value. This is around 600 watt per meter square. Considering irradiance at Mars, at Mars distance to be 1.52 AU. And in question 14, what is the mean solar irradiance at Earth? If mean solar irradiance at Earth is to be 1360 watt per meter square, what is the fractional change of irradiance between perihelion and aphelion, where perihelion is a distance of about 0.983 AU and aphelion is at the distance of 1.016 AU. So this is the most minimum distance between the Sun and Earth has the term perihelion, and the aphelion is the maximum distance between Earth and Sun orbit. So you have to find the distance, the S value at this perihelion and aphelion, considering S0 to be 1360 watt per meter square. Question 14 is this. Yes, question 13, correct? What is in the percentage unit? Uh, so fractional change can be given as so the word S0 by aphelion, there was S0 by 0.983 square, and sorry, perihelion and perihelion is 1.016 square. So this is coming to be 0. This difference is coming to be 0.066 S0. So I am considering the fractional change, that is this by 0 into 100%, that is about 7% change is seen for this two position. Yes, 6.6. Now question 50. The daily average solar insolation at latitude phi and solar declination delta is given by this formula, is equals to q is equals to s0 by pi r0 by r square, and some terms with the phi and delta, and also h. H is
It
the
is not visible, ma'am.
uh, no,
Question number 15.
15.
Excuse me.
Is it visible now?
Yes.
Okay.
Yes, thank you.
Yes. Okay. Now, daily average solar insolation at latitude phi and solar declination delta is given by this formula, where delta is the solar declination, phi is the latitude of the position at Earth, and h is the hour angle, H is the half day length angle, and this factor R0 by R square, this represents what? Solar zenith angle dependence, seasonal declination effect, orbital distance correction, and atmospheric absorption. We will not derive or check anything about this formula, but we have to just have some intuition how this R0 by R factors comes. You can mark this question from your intuition. What kind of correction is R0 by R? So this R0 by R factor gives the correction of the orbital distance. Now question 16. The surface irradiance is reduced with angle by what factor? Cos theta, sin theta, 1 by cos theta and tan theta. Question 16. Surface irradiance is reduced with angle by what trigonometric factor? Cos theta, sin theta, 1 by cos theta and tan theta. Yes, this is the cos theta, just from the trigonometric contributions. Now question 17. Sun spectrum is the black body spectrum. So a black body spectrum, all kind of wavelengths contribute based on what is the surface temperature of that black body or the emitting surface. Now sun has a black body spectrum, which picks up around within 500 to 600 nanometer, and this sun's black body spectrum do change with the solar cycle, that is the 11-year sunspot cycle observed in solar due to the sun's activity. Now your question is, which part of solar spectrum show the largest relative variability due to solar cycle? Visible spectrum, near infrared spectrum, ultraviolet spectrum and the microwave spectrum. Which part of solar spectrum shows largest relative variability during the solar cycle? Visible, near infrared, ultraviolet and microwave. Which part of solar spectrum shows largest relative variability?
Is it UV then?
Yes, this is UV. Question 17 is UV. And also can you with the wavelength, can you place this spectrum, this regions? In wavelength, you have to write what is the ascending order of wavelength. What are the zones?
Less than 400 nanometer.
Yes. So, what is the ascending order of UV wavelength here? You have to place this ascending order of UV wavelength. First comes UV, which has most lowest wavelength and high frequency. Then comes visible. Then comes near infrared. Then comes microwave. Microwave is the largest wavelength, or largest wavelength means lowest frequency. In question 18, irradiance versus insolation, Ashran, and what is the main difference between irradiance and insolation? There is no difference between these terms. Irradiance is instantaneous solar flux, and insolation is the time indicated energy received by flux. And insolation is flux, irradiance is total energy. Both mean albedo. What is the difference between irradiance and insolation? Now the definition, basic definition of three things: solar constant, solar irradiance, and the solar insolation. So solar constant, you know, that is the flux or the reference flux that is received due to sun at the top of atmosphere perpendicular to sun, and considering the sun and earth distance to be 1 AU and the output from the sun, one can derive the solar constant, and this comes around 1360 to 760 watt per meter square range. And the solar irradiance, this term defines the instantaneous flux received at some particular location of earth. So this solar irradiance value of course varies with angle and also the time or season when we are observing that location, and also the atmospheric factors. And the solar irradiance has the same unit of the solar constant, that is watt per meter square, and it has typical value of 1000 watt per meter square, 0 to 1000 watt per meter square at the surface. And the solar insolation defines the time integrated solar energy received, and often this is defined by the joule per meter square or kWh, kilowatt hour, kWh meter square per day. And this has value of at the mid latitude, this has about some value. We will not consider these values now, but solar insolation and the solar irradiance, both two are the different term. Solar insolation is the time integrated solar energy that is received by sun, and received from sun at earth's location, particular location, and the solar irradiance is the instantaneous flux at this location. So question 18, option 2 or option B is correct. Now question 19, at zenith angle theta, zenith is when you are at some earth's location, the top is your zenith, you know, and you are when you just at the angle theta, the optical path to the atmosphere is proportional to 1 by cos theta, sin theta, and tan theta. So you can, if you draw the atmosphere with the same height, you can see, sorry, you can see the height of the atmosphere is not same in the full region, it varies. Now the optical path to atmosphere is proportional to what factor? Cos theta, 1 by cos theta, sin theta, and tan theta. You can unmute yourself or you can write in chat box. So now you can consider this image. You are at some Earth's position. If Earth's atmosphere is at a shell-like structure. Now, if your optical path length is 1 at your overhead, and now if you go to a place which is at theta z, or the theta from angle from the zenith. Now here the optical depth increases, and this is written by 1 by optical depth is 1 by cos theta factor in and now you can say that at zenith theta is equals to 0, your optical path length is unity if, and when theta is equals to 90 degree, your optical path length will be in infinity. Now question 19, option A is correct. Question 20, the interstaitious solar flux at the surface under clear skies at noon can reach up to 1000 watt per meter square. However, the global average at surface is found to be about 170 watt per meter square. This difference is mainly observed due to orbital eccentricity, solar magnetic activity, spherical geometry of Earth's surface, albedo, and atmosphere. And option D adds the ocean heat uptake. Question 20, interstaitious solar flux at surface at the clear skies at noon reach up to 1000 watt per meter square. However, the global average value at the surface is about 170 watt per meter square. This difference comes due to what effect? For the eccentricity, solar magnetic activity, spherical geometry, albedo, and atmosphere's all total contribution, and D is the ocean heat uptake. Yes, the correct option will be C. The spherical geometry, albedo, and atmosphere, both three have effect. Which wavelength is the most strongly absorbed, reducing the surface irradiance? Visible, ultraviolet, near infrared, and radio. Which wavelength range is most strongly absorbed, reducing surface irradiance? Visible, ultraviolet, near infrared, and radio or radium. Question 21, option C is correct. The near infrared is more strongly absorbed. Question 22, daily mean insolation at latitude phi and solar declination delta is proportional to what factors? Here h is the same h which was discussed here, that is the half day length angle, and we will not discuss how this equations come, but also daily mean insolation has dependence on three factors. One in h, one is phi and delta, and any of this option containing this three will be the right, which have the three kind of dependence. You have to choose that for this kind of questions. Question 22, option 2 is correct. Question 23, I will skip 23 for now because but question 24, these are the same kind of questions from the previous discussion at our class. Considering the albedo of Mars to be 0.2, find the emission temperature of Mars. This is the mathematical question. Considering albedo of Mars to be 0.2, find the emission temperature of the Mars. For this question, you can write that you have to find that is 0 at Mars. Then you have already calculated it to be some value 588 watt per meter square. Now you have to what amount of the shortwave radiation that is received going in the through the Mars surface, so through the Mars atmosphere and received in the surface is will be S0 at Mars by 4 into 1 minus alpha. So about 0.8% will be going downward. So that will be balanced by the emission temperature, that is sigma TE to the power 4. Considering albedo of Mars to be 0.2, find the emission temperature of Mars. Okay, I'm just checking what was the value. Yes. Yes, it is coming around 213 Kelvin, that order. 313 or 14 Kelvin order. And next question is let the three cases of hypothetical atmosphere for the three hypothetical planet, and both the three planets' emission temperature to be 15 degrees Celsius. They are made up with in layers of atmosphere. All the three has the in layer of atmosphere, suppose, and in can be any different value for the three. But in for first case, consider that in and that is different number in 1 and 2 and 3, and they are trapping heat due to the greenhouse gas. Now the surface temperature of this three planets, or planet 1, planet 2, planet 3, are 30 degrees Celsius, 5 degrees Celsius and 80 degrees Celsius. Now you have to check which cases can be possible here. Planet 1 possible, is planet 2 possible, or planet 3 possible? Considering the equation which was discussed for the in layer atmospheric model of greenhouse. And of course they have the greenhouse gas, and you have to consider the atmospheric model, in layer atmospheric model. So in the in layer atmospheric model, we had seen that the surface temperature and the emission temperature have this relation, that Ts is equals to Ts is equals to n plus 1 to the power n plus 1 to the power 0.25 or n plus 1 to the power 1 by 4 and Te. So one can write the n's value to be Ts by Te to the power 4 is equals to n plus 1. So Ts by Te to the power 4 minus 1 is equals to n. This formula comes. Now if n is greater than 1. That to be, there is of course the surface, one layer surface. Then n is greater than 1 if, then ts by te to the power 4 must be greater than 2. So for this kind of any planet that this in body approximation to be possible, you have to be ts greater than equal to 2 to the power 1 by 4 into te. Now this 2 to the power 1 by 4 or t to the power 0.25, this factor comes around 1.19. So for any in layer approximation or in layer model, you have to be the ts must be greater than 1.19 into te, or 1.2 times ts must be greater than 1.2 times te. So in the first case, this question, ts to be so from this model, our ts should be greater than 1.2, or specifically 1.19 factor is coming, ts is equals to te. Now for the first case, our ts, emission temperature we are keeping same, te is equals to te1 is equals to 15 is equals to te2 is equals to te3, but ts1 is 30 degrees Celsius, so ts2 is equals to 5 degrees Celsius, ts3 is equals to 80 degrees Celsius. So this one is equals to 5. So you have to find this factor of ts1 by te. So for this first case, this factor is coming around 30 ts te. So ts by te, ts should be greater than 1.2, ts1, sorry, ts must be greater than 1.19 into te. So 1.19 factor to te is coming 1.19, 1.2 times te, that is around 18 degrees Celsius. So critical value S1 T TE TS minimum would be 18 degrees Celsius. So first case is possible, second case is not possible, third case is possible. So for this kind question, this question you have to
Excuse me, ma'am.
yes,
I think only 80 degrees is possible.
yes, 30 should not be possible, I guess, but here what
Because
if
it is the critical value.
30, Ts surface temperature is 30 degrees Celsius. But what are you getting critical value? Critical value are you getting? Two to the power 1 by 4. 2 to the power 1 by 4. Sorry. 2 to the power 0.5. That is 1 point.
Nuclear value is around 72. Oh,
Ts by Te to the power 4. This should be around 72, but why I am getting this? Because while I was using 30-degree Kelvin, I was not getting n greater than 1 also. So, yes, Ts by Te to the power 4 minus 1 must be greater than 1, greater than 2. Ts by Te to the power 4 2 to the power 0.25 Te. Emission temperature is, first one should not be possible, I guess. From the first one, if you can use this formula, then 303 by 288 to the power 4 minus 1, this is around
but
0.22.
it becomes negative.
Huh?
N
Yes,
becomes negative. N becomes negative for 30 degrees centigrade.
yes,
That's
n
it.
becomes negative for 30 degrees Celsius. 30 for, so you can use this, but how this equation, n must be greater than 1, how this argument can be incorrect? I have to check how it is, why this argument is becoming incorrect. But if you use this plugin only the values here in this formula, then you will get the values of the n less than 1 for first two cases, but in the third case you will be getting n greater than 1. I have to check that. Sorry for the mistake. I have to check this argument. Now question, sorry. Lay another hypothetical planet. Suppose emission temperature is minus 15 degrees Celsius and that is made up with in layer of atmosphere trapping heat due to greenhouse gas. Surface temperature is 55 degrees Celsius. Now what is the value of N? So you have to use this formula, that is our Ts is equals to minus 15 degrees Celsius that is 273 minus 15 is equals to 258 Kelvin, and emission temperature is 55 degrees Celsius. That is 255 plus 273, that is this comes around 328 Kelvin. Now you have to give the TS uh, by PE. Emission temperature is minus 15, sorry, emission temperature is 258, but surface temperature is 328 Kelvin. So Ts by Te to the power 1 by 4, Ts 328 by 258 to the power 4 minus 1. This is about a single layer atmosphere, not getting the value in, I'm not getting in value greater than 2, but
Air is coming 1.6, so air must be 2 layer.
uh, yes, that should be if 1.6 you can check the what is the in the given MCQ options. 1.6, yes, 1.6, I guess this should be 2 should be correct. Now question 27 I am skipping today, and question 28, there is a statement, you have to mark true or false with this question. No absorption of electromagnetic radiation is likely to happen for the molecule's vibrational frequency and the temperature, the electromagnetic radiation's frequency. This statement is true or false?
False.
Yes, this question is false. We will discuss the thing after this discussion. 30, 29, 30, 31 with the all. And in the 29, the probability of photon absorption at frequencies slightly differ from the harmonic vibrational frequency. This is observed due to isotropic substitution, collisional energy exchange, higher order harmonics, and the quantum tunneling. Probability of photon absorption at frequencies slightly becomes different from the harmonic vibrational frequency. This occurs due to isotropic substitution, collisional energy exchange, higher order harmonics, and quantum tunneling. Question 29 option 2 is correct. The collisional
Maybe
energy
isotropic.
Question 29, I guess.
Okay.
To a collisional energy exchange is the main thing for the photon absorption frequency change. In question 30, pressure broadening is most dominant in which layer of atmosphere? Troposphere, stratosphere, the lower layers, the thermosphere, the mesosphere, or the exosphere?
Option 3.
Yes, pressure broadening is observed due to the particles density. So its particle density is high at the lower two layers. So troposphere and the stratosphere are the options which are correct. Question 31. Which spectral feature is primarily shaped by pressure broadening in the Earth's atmosphere? Narrow absorption lines, absorption bands with peak shape distribution, sharp emission line, and blackbody continuum radiation. So now we can answer 31 or 29. Check this answer after this statements. So when in a gas phase, molecules in the gas phase, molecules move out. This is the called the transitions or the translations, and rotate about the same axis. That is called the rotation, and can vibrate like the masses of spring, known as a vibration. If a molecule is made up with different kinds of atoms, that is about suppose CO2 or H2O, that kind of molecules, they have the strong dipole moment, and its rotation is caused by fluctuation in the electromagnetic field that can resonate with the certain frequency bands of electromagnetic radiation. Hence, the molecules like the H2O or nitrous oxide or CO2, they absorb the electromagnetic radiation or the black body radiation that is coming from the sun over the certain frequency ranges, which energize the molecules dipole moments to oscillate. Furthermore, these molecules tend to vibrate at certain specific frequencies. These certain frequencies are known as the harmonic frequency. When electromagnetic radiation at the frequencies close to this vibrational harmonic frequency incident on the molecule, then resonance occur and the corresponding vibrational harmonic mode is get activated by the absorption of that specific frequency in the electromagnetic wave band. So for this first question of the question 28, we told that the absorption is happen when the vibrational frequency and the radiation frequency or the electromagnetic frequency uh, matches. And also for the isolated molecules, one would need photons of exact frequency as the vibrational mode frequency for the absorption to occur. The molecules of the gas in atmosphere collide continuously with each other, and this collision act or remove energy from the molecule itself. This collisional energy distribution can allow the radiative activation of vibrational mode to occur over the broader range of photon frequency. This allows the absorption lines to broaden into absorption bands with a peak-shaped distribution of photons with frequencies slightly larger and smaller than the harmonic frequency will also have a finite probability of getting absorbed, as the collision can add or subtract the requisite energy mismatch during the absorption process. This collisional induced broadening of absorption line is called the pressure broadening, and this is the dominant phenomena in the troposphere and the stratosphere, where the gas pressure is high enough so that the molecular collisions becomes more frequent. So in question 30, the pressure broadening is most important in the troposphere and the stratosphere, and which factor features primarily shaped by pressure broadening in the Earth's atmosphere. These are the absorption bands with peak shape distribution. So here this is because here in this week 5 or week 5 content or week 6 content, you will get the idea that this also this as the frequency electromagnetic for this new vibration, new EM and new vibration, there is probability, and also there is another probability for that comes from the uh, frequency slightly larger and smaller than the harmonic frequency, uh, because this can subtract and add the requisite energy, and also there is a this mismatch can be possible due to the pressure broadening. So for the question 31, the absorption, the pressure broadening thing shape the band, absorption band with the peak shape distribution. So in pictorially you can view that frequency, this vibrational frequency or the this vibrational frequency. If this is a spectrum, that is the flux versus that's the radiation's flux versus, suppose this is the inherent distribution of the spectrum, that is the flux versus frequency. uh, this is not a delta like function. Always you will see the absorption like this thing, or sorry, this thing. You will see the creation of band due to absorption. Question 31, option 2 is correct. Question 32, which statements are correct? Carbon dioxide contributes to cooling in stratosphere. H2O is the significant contributor of the shortwave heating in the troposphere. Ozone is primarily responsible for the shortwave heating in the troposphere, and water vapor dominates long wave cooling in troposphere. CO2, H2O, O3, DUBO, all those are not coolant. Which of the statements are correct?
Option 4.
Now we will see about this thing. So carbon dioxide contributes to cooling in stratosphere. True, in the thin low pressure stratosphere, carbon dioxide efficiently infrared to space, thus provides some net cooling. And H2O is the significant contributor of the shortwave heating in troposphere. This option is true because water vapor absorbs solar near infrared and so contributes to the shortwave heating in troposphere. Ozone is primarily responsible for the shortwave heating in troposphere. That is false. Ozone strongly absorbs UV or the shortwave. Heating is mainly in the stratosphere. In the troposphere, the shortwave heating, there is ozone content is very small. No shortwave heating is possible. Oxygen, water vapor dominates long wave cooling in the troposphere. This is true. H2O is the main emitter or absorber in troposphere, so it dominates the long wave cooling.
Excuse me, ma'am.
Yes.
Option 2 and 4, I think it is contradictory.
2 and 4.
Option 2
H2O
water
is the
vapor actual very infrared emitter. And option 2 is for short wave, not long wave.
yes. I am not very much sure for this question. I will solve this question in the next week. Is it okay?
Okay.
Okay. Then question 32 I am leaving. And then I guess the question should be removed now. I am removing this slide today. Um, Question 37 and 38. These are the two last questions for today. And question 37 is water vapor determines the lapse rate in troposphere. This statement is true or false? This statement, this statement is true because water vapor is the dominant greenhouse gas. Yes, the water vapor is dominant greenhouse gas and strongly controls the moist adiabatic lapse rate in the troposphere region. In dry troposphere, the lapse rate is dry adiabatic lapse rate, and this dry adiabatic lapse rate value and the water vapor present, it will release the latent heat and reduce the effective lapse rate. And the moist adiabatic lapse rate, that value comes around 4 to 7 Kelvin per kilometer. So water vapor determines the lap stress structure in troposphere. This statement is correct. Now for the question 38. Suppose you have a ground. Now you have an atmosphere. So it is a single layer atmosphere, suppose, and it has infrared emissivity epsa, and it is transparent to short wave, that is of course S0 by 4 into 1 minus alpha. That radiation, that short wave radiation, is coming to the ground, and now ground is emitting at Ts, atmosphere is emitting at Te, T, not Te, Ta, and Te is the emission temperature of the system. Now derive the Ts from the with S0 A and this infrared with the infrared emissivity factor. These are the same question which was derived in the class, in our lecture. So now the main thing. So this is the system where the Ts is the surface, S is the surface, Ts is the surface emitting temperature, Te is the Ts is the surface temperature, and Te is the emission temperature of the system. So one can write that sigma Te to the power 4 is equals to S0 by 4 into 1 minus alpha. Alpha is the our albedo, and epsa is the emissivity of this atmosphere. So you can check that atmosphere will be radiating upper region and also the lower region. So atmospheric, considering atmospheric emissivity to be epsa, you can write the two total absorbing emissivity due to this atmospheric layer is 2 epsa Ta to the power 4, 2 sigma epsa Ta to the power 4, that this factor coming 2 times. And also this outgoing long wave radiation, that is coming from the two parts. The first part, you know, that is the epsa sigma Ta to the power 4, and another part, that is 1 minus epsa sigma Ts to the power 4. Now why this 1 minus epsa factor comes? Because we know the a layer has some emissivity and some absorbivity. Absorbivity and the emissivity both are same for any black body emission. So the Ts sigma Ts to the power 4 which was emitted from this ground or the surface, that that cannot fully go outside. So you have to check that 1 minus epsa factor only can go outside, and less and the other factor, that epsa sigma Ts to the power 4, this factor get absorbed by the atmosphere. Now if you can if you write the three equations, then you can check that the Ts, this value is coming to be the net value where 1 minus epsa by 2, or the epsa is the emissivity of this absorption atmosphere comes. Now if epsa is equals to 0, then you can just write the equation to be this format. Question 34. Okay. So this was the last question for today. I cannot discuss some of this question today, like 32 to 36, and also could not give the Ts to the this Ts details, this n factors details. I will try to discuss those in the next class. If you have any question, you can ask. I'm stopping the presentation.
Yes, ma'am. Can you explain the vibrational frequency?
Uh, Vibrational frequency. Vibrational frequency. Vibrational frequency in what terms? I mean,
How it generates or from where it is? What
huh?
are their range?
Yes. How they generate means suppose. Okay, I will try
This
to.
is basically molecular vibration frequency,
Okay,
right?
I will try to
Number one,
explain molecule. Yes, you can check.
molecular vibration frequency.
Okay, I will try to get the details in the next class because if I give some pictorial representation for that, that will be very useful, I guess. Uh,
Okay, ma'am. Thank you.
okay. Hmm. Yes. Any other question? If not, then I am stopping today's presentation. Thank you for joining. Okay. Thank you for joining.
Okay, thank you, ma'am.